In this video, we're going to learn about solids. So in solids, all the particles tend to stay in pretty much fixed positions. And so that means that if I've got, say, several particles here, their kinetic energy is going to be expressed mostly in vibration. Whereas gases are actually translating through space. They're moving around in space. And liquids as well, they tend to flow across each other. In fact, both liquids and gases are considered fluids. Solids, by contrast, won't flow across each other. They will, the particles will stay mostly in exactly the same place, and the difference between a hot solid and a cold solid is simply the amplitude of their vibration. If a solid is hot, the particles will be vibrating more, but they're not going to be moving across each other. They'll just be vibrating more. So in solids, the intermolecular forces are really, really strong, which is why the particles don't flow past each other, which is why they're stuck in place. And because of all this, solids will have a definite shape and volume. If I were to take this little block right here and I put it in a container like this, well, maybe like this so that it's on the bottom of the container. Notice there's some space on the either side of it. If this were a liquid, it would kind of flatten out and occupy the full width here. But the shape of a solid is not going to change based on the container it's in. Additionally, the volume isn't going to change as well based on the container that it's in. So if I were to close this container, it's not like the particles are all going to spread out across the full volume. That's what would happen in the case of a gas. We can say that solids are pretty much stuck in having a very high density, and so they can't compress. They also really won't expand either. And that really stems from, again, the intermolecular forces that hold the particles together and cause them to not just spread out and occupy the volume of the container they're in. Now, solids, there are several different types of solids. The four that you can see here are all crystalline solids, and that's the vast majority. There are ionic crystals where the particles are individual ions, like sodium chloride, where you have precisely sodium cations with a +1 charge and chloride anions with a full-on -1 charge. And you can see that their melting points are pretty high. In general, we've talked about this actually in previous units, the melting point of an ionic crystal really depends on Coulomb's law. The more charged the particles, the more charged the ions, the higher the melting point. The smaller the ions, the higher the melting point. So if you had something like magnesium oxide, where the oxide is smaller than the chloride and the magnesium is similar to the sodium, but both of them are 2 ions, +2, -2, I think the melting point is like 3,700 degrees. In the case of network covalent crystals, the structure of these is quite interesting. This formula that you see here, silicon dioxide with a subscript of X, that just means that there is a continuous pattern of SiO, SiO, and I'm just drawing it linearly here, where you have this continuous structure. And what's interesting here is that I'm drawing what look like covalent bonds. They are not intermolecular interactions that we're seeing here. What we're seeing is full-on covalent bonds. And so the reason why the melting points of these is so high is that in order to melt them, you have to break covalent bonds, which of course are very, very high energy bonds. And I'm going to stop continually drawing these here. I think that you get the idea. We just get this continuous pattern. If you take a crystal of SiO2 with that subscript of X, this will be just one massive, massive molecule covalently bonded. And if you're wondering what this is the formula of quartz, the crystalline mineral quartz. So again, super, super high melting point, because in order to melt it, you're really breaking covalent bonds, which are high energy. Third, we have metallic crystals, and in the past we've studied metals. they tend to have high-ish melting points, which also depends on how many electrons there are in the valence shell that are involved in this delocalized electron cloud. And finally, we have molecular covalent compounds like NH3, and you can see here the melting point is ultra low. So if we do have NH3, this is not some kind of macromolecule as in the case of a network covalent. It's not a metal where there's delocalization, and it's not an ionic compound where you have full-on positives and negatives. You do have hydrogen bonding between one N in one NH3 and the H in another NH3. And so that is a fairly strong intermolecular force, but that is still not enough to make this have a very high melting point. It's still very, very low. And if you were to take other molecular compounds, maybe something that's slightly polar but not this polar, the melting point's going to be even lower. And if you have something that's nonpolar and only has dispersion forces, the melting point is extremely, extremely low. Take, for example, carbon dioxide. Actually, you'd have to play around with the phases a little bit. It sublimes at negative 78 degrees to form a gas, actually. So once carbon dioxide hits negative 78 degrees, it goes from the solid straight up to gas. So suffice to say, whenever there's a covalent molecular compound, the IMFs are going to be very, very weak, and you'll have a relatively low melting point. Finally, okay, we have four examples of crystals. There is another category, and these are called amorphous solids, examples being glass and plastics. Amorphous means without shape, and so indeed they have no definite shape. An example is glass, which actually has the same chemical formula as quartz pretty much, but the way it's cooled from liquid to the solid phase causes it to still kind of flow. And if you were to go to, for example, like a really, really old cathedral, you'd actually find that the stained glass windows that they are thicker at the bottom because gravity has caused the stained glass to flow downwards a little bit and kind of bunch up a little bit more at the bottom. They are by no means liquid, but they are strange. They are strange in the sense that they kind of flow and they feel a little bit like liquids, except, man, they take forever to flow. But if you raise their temperature, even not to full-on melting point, that does make them a bit more pliable. And that's why plastics, even before melting, they're quite bendy. So that's it. Those are all the different types of crystalline and amorphous solids. Hope this video has been helpful. Let me know if you have any questions or comments in the comment section below. Thanks for watching.